Right, starting off with something new. We have the NRTL expression or equation, the non-random two-liquid model. Basically, what this is doing is modeling some non-ideality for our mixtures, eventually helping us to predict phase equilibria. As you can see in the expression here in the bottom, it does depend on the liquid mole fraction and some other parameters. We have G, tau, and obviously X for a liquid mole fraction. But essentially what we're going to be doing today is modeling this in Python. We have a repository in GitHub that we'll be grabbing some parameters from, namely this tauij equation. And these are the binary interaction parameters that are imported from ChemCAD. Uh, Essentially, it's a public chetools. This is not ChemCAD, but the GitHub repository. We'll be importing from chetools these binary interaction parameters and using those in Python, basically. The rest, tau, I believe, well, it's given by this equation in the middle here. And G is this expression where we're multiplying alpha, another parameter that we grab from our repository by tau. And obviously all these operations can be done in Python. We're just going to be doing some, well, grabbing the data from the repository. Then we have our kind of monstrous expression here where we're going to be modeling our well, activity coefficient. The X, tau, and gamma or G we'll be using matrices to kind of do the operation with the indices. So there'll be some well, straightforward matrix multiplication, or I'm sorry, straightforward subtraction, division, but also a matrix multiplication, which is essentially a dot product. And you'll see those from as we kind of break these indices down. But like just a quick overview on like what the activity coefficient is. So it's kind of relating the binary interaction. So it's saying how these pairs of molecules essentially interact is dependent on or proportional to their local concentration. So if you will say you want something to react, well, you want to make sure those local concentrations are relatively the same, such that, well, they appear next to each other at a certain probability. And that's basically what this activity coefficient is saying. And part of that non-ideality comes from this, I guess, theory. Excuse me, theory. Um, so, yeah, I guess kind of jump into it. So, what we have here, I'll go ahead and switch to my split screen here. Oh, I guess we're already on it. Awesome. Um, so yeah, actually that's not what I want to look at. So let's go, where did it go now? Um, Give me 1 second here. There we go. All right, sorry about that. So again, just from the Wikipedia, I kind of read through this if you want on your own, but this is the main expression, basically that same screenshot I had before. Hopefully that's big enough. And then what I have here on the left is our template. Basically, we're going to be grabbing from the repository. This line of code, or all these lines of code, basically allow us to import from the notebook chetools and kind of access all the data here using any of the functions that are pre-written. And then I also have the NRTL parameters right there, which is, as you can notice, different from the tau defined by the Wikipedia page. And what this basically comes down to is the fact that there isn't enough data to correct these parameters. Wikipedia is pretty generous, assuming that we do have some enough data to make these parameter calculations, but obviously from our import in ChemCAD, which is now visible in our repository here, you can see a lot of these parameters are in fact 0. So again, that comes down to the data where essentially someone is analyzing component mixtures of, well, these binary interaction pairs what we're doing today is isopropanol water. So isopropanol is 36, water is 30. So if we scroll down and find that interaction pair, 30 and 36, that's our parameters right there. And after someone analyzes those vapor liquid equilibrium and the predicted mole fractions or compositions, essentially what they're doing is comparing the predicted compositions from the NRTL model and the experimental one, and basically doing a minimizing that sum square error or deviation, which is basically a nonlinear regression, to correct for that difference in predicted versus experimental. And that's how those parameters are achieved. And obviously, if you don't have enough data, then it doesn't make sense to go all the way to define even more parameters than what already makes sense. So that's the little explanation on why these don't match up. And yeah, I think we can go ahead. Actually, I think I just copied this. So let's go ahead and name this, I don't know, NRTL. And we can go ahead and let's just run this, make sure it's going, and do what we normally do. So we have to create our properties. So p equals props for our desired components. So I said isopropanol water. So let's do just that. Isopropanol and propanol, comma, water. And you'll kind of see here, well, I guess I should show you that from our chetools, this gamma function is kind of already defined. So we can kind of check if this is correct. So what we'll be doing to kind of see what the correct answer is already, well, technically this should be after P, but I'll put it up here so I can actually, I don't know what's the word, just show it, and we can scroll up to get the right answer, see if we got the right answer. So what this is NRTL, and then gamma for our activity coefficient gamma. And you'll see, I wonder why it's not letting, show me the inputs, or maybe I mistyped. Let's see. Let's do that. And then maybe now. There we go. So now we go to gamma, and you'll see that it takes an input of x and t. So x is our liquid mole fraction as seen in this equation or expression, and then t is our temperature. So in the end, you'll know that we'll have to have those as inputs. So we should initialize those. I guess I could put it down here. So if we, well, let's go ahead and do that. We have our liquid mole fractions, an array of some numbers which add up to 1. So we'll have isopropanol at 4. Let's not make that in quotes. 0.4, and then 0.6 for our water. Again, these are arbitrary. I feel like, or I think in the future we'll be doing like 4 mixtures, like we did in class, but I'll keep it simple for now, so I can check it pretty easily. And then what else? I said the temperature as well. So temperature hard coded. Again, I'm picking something I've done in my notes and checked before. So I'll do 350 Kelvin and make sure this temperature is in Kelvin. That's what our input is taking. So we need to make sure that match. But just to note that that temperature is Kelvin. And if I plug those in, we'll have our numbers that we want to get. Oh, I didn't shift enter at the top. So these are the activity coefficients for the corresponding isopropanol and water. So at the end, when we're finished coding this whole thing out, we know what to get here. So I'll just keep this right hand. I'll focus in on this, why not? So zoom in a little, like so. Still recording, pretty cool. So yeah, to code this out, we'll go ahead and remember we had our G, our alpha, and our tau. So alpha was already, if you look in our given functions here, we already have alpha, and then tau is composed of these other coefficients A, B, C, D, or parameters, I should say, and those go to this corresponding equation before. Remember, this was just from our repository. So again, I'm just going to be pretty much coding this out exactly. So I'm going to go tau is equal to that, and I'll copy this so it goes a little faster. But essentially, it's NRTL A, and then we add our B parameter. It looks like that's divided by temperature. And then we add our C parameter times. Now for Numpy, we use log, and now you see there's a difference between log, which is actually natural log, and then log 10. Don't ask me why, I don't know, but we can kind of see here pretty simply. If I try to take the natural log, remember this is natural log of an exponent 1, well, these are just going to cancel out, so we know that is actually 1, so this has to be obviously natural log for that to happen. If I did log 10, obviously not the case. So we know this is natural log, just so you know, for reference. So what is that? Cut that off there. So that is natural log of t, so parentheses t, plus, again, that is parameter d for the NRTL, and then times temperature. So that should be our tau. Go ahead and display that, make sure. So yes, it is a 2x2 matrix. Because we have two parameters, we'll have two two numbers, I should say. So it's a 2x2 matrix, and you'll see with increasing the number of components, you know what, why not do it? Oh, I think acetone was one of them as well. So acetone, then I'll have to kind of change the x so it corresponds. So I'll do 0.1 and 0.3, so it still adds up to 1. Shift enter on all of that. Now we have a 3x3, and obviously our gamma function will return 3 as well. So obviously different numbers, so we'll want to stick with, well, I guess I will want to stick with what I know. So let's go ahead and return that back to normal, like so. Next we had, well, alpha, remember, was already part of the functions we could call here, from properties, props. So, well, I guess it's NRTL in this case, but gamma was the next one, and I believe, or I'm sorry, G was the next one, and I believe if I move this over, do something like this, we'll see that G is indeed the exponent. So I'll go ahead and just leave that up there. So we have G is equal to exponent, so we use Numpy exponent, and then that is negative. So our alpha term, so alpha, I guess I just typed it, so wondering why it didn't show up, but that's okay, and times tau. Go ahead and display that, make sure that's still a 2x2. Awesome. So hopefully we did everything right there. I'm kind of curious why that's not showing up, but if I do this, it should be, yep, it's there. So we should be good on that part. So yeah, I think we can kind of go ahead and start to tackle this expression here. So I guess we could start with the most simple one here, which is x times g. So if I zoom in a little, you'll see that it's a x with an index of k times a g with, now this is two indices, so we'll think of these as two-dimensional matrices, where x is just a one-dimensional array with k elements. G is a k by I matrix. So we'll kind of see that as I draw this out, and I'll switch over so we can do just that. If I can find it, there we go. So going back here, yeah, I had it here anyway. So we'll start right here for our operations that we'll start defining. So it won't be too long. So essentially this is x times g, so I'll write this out down here again. This is x k, g k I, and what we're going to want to do, well, I'm kind of spoiling it, but this is essentially a dot product. What we want is, well, I guess I can define how many components we have. Well, we have two components, isopropanol water, And what this ends up being, well, we know G from what we did earlier is a 2 by 2. And X, we define the liquid mole fractions as a 1 by 2. Well, technically it's a one-dimensional array with 2 elements, but that only helps our case here. So it's something like we'll have our array of X, which is X1, X2, and then we'll have our 2 by 2, which is, I guess we can write it like this. So row 1 and column 1, and row 1, column 2, and then we have row 2, column 1, and then row 2, column 2. Just making sure that my voice is still getting picked up. Okay. So again, this multiplication, well, we know it's essentially a 1 by 2 by 2 by 2. And when we do the multiplication, or I'm sorry, dot product, we take the outer indices. So the way we want to do this, well, I guess I should mention it is a sum, so that's why it is a dot product. So instead of just multiplying across, we have, well, it's not going to be across, but it's going to be mapped so that the k's match for one index of I, and then the k's match for the other index of I. So I guess it might be helpful to show something like index 1 and index 2 for the i's. And obviously k is the rows, but you know what, I'll do it. So k equals 1, k equals 2. So can't really see that well. Sorry about that. I'll use red. K equals 1, k equals 2. Well, that's pink, but whatever. I don't know, I kind of wrote over it, but I don't know, this might be overkill. But basically what we're going to do, since it is a sum, we're going to be matching, well, when k's are equal. So when k is 1, we have x1, and then times g1, so k is 1, and then we keep the I constant, so we'll start with 1. And since it's a sum, we do the sum of the next iteration of k. I believe the summation was k, right? Yeah, k to n. So obviously you start from k equals 1 to n. So after 1, obviously you have k equals 2. So k equals 1, k equals 2. So you have x2 times g2, and keeping the index the same, it's still 1. So this is for index I equals 1. And obviously we're going to be adding that, or I guess not adding that, but the next component of that will be I equals 2, where now k, you do the same iteration of k equals 1 and k equals 2, except now the only difference is the i's are changing to 2. So doing something like that, we have x1 times g1, but now index of I is 2, so 2, plus x2 g2, but now index is 2. So it's basically, if you want to look at it visually, we take our x. What happened here? Okay, froze. Hopefully that was still caught. But here's that work just in case. So you take our x matrix and multiply it. What did we say? G1 and G21. So you take it along the first column, and then we take our x matrix again, and we multiply by the second column. So those will be our two numbers that we get in our one corresponding, or I guess our output of 1 by 2. So essentially, I don't know if you want to call this A, call this B. So then our output is just simply AB. Hopefully that makes sense. It's a dot product, which at the end of the day is called a matrix multiplication. So we'll be using the @ sign in Python to cover for that. There we go. Okay. I think that's all I want to say. I guess it doesn't hurt now to just cover all of the, so I'm not switching back and forth, cover all the different matrix multiplications. So this will be our xg. We'll be denoting it as something like xg is just the matrix multiplication of x and g. Yeah. And then we'll go up to this next term at the top, this numerator. So not too much has changed. Now we have inclusion of t, or tau. And if you remember, tau and g are 2 by 2 matrices. So that's just a straightforward matrix, or not matrix multiplication, but a straightforward multiplication. in which case we match up the different, well, I guess corresponding, I don't know what you want to call them, but like pairs or coordinates. So we have tau. I guess I should just put tau. Is it Ij? I believe it's still Ij or Ji. So this was Ki. This is Ji. Don't let the indices confuse you. At the end of the day, they're kind of the same values, just being iterated in a different way. So tau Ji, Gji. So tau, not do tau for some reason. Tau Ji and G Ji. So these are 2x2 matrices. So 2x2. And I mean, might be overkill, but I'm gonna do it anyway. So tau, tau. We have 1, 1. Again, rows and columns are denoted from left and right. So in this case, J is rows, I is columns. So row 1, column 2, row 2, column 1, row 2, column 2. And G is pretty much the same as what we had before, whereas I'm just going to copy it down. Same as the left. And basically, again, it's a straightforward multiplication where we match up the different coordinate. Well, wherever they are, they get matched up with their corresponding positions. The other matrix kind of mirrored, if you want to think about it like that. Like if you flop them into a sandwich, they'll come out the same way. So I don't think I should. It might be overkill. I think I'm already going overkill with these straightforward multiplication. So this will be our tau times G. So very straightforward because our matrices match here. So this will be tau G, tau times G. And if you remember with x G, where we did a matrix multiplication, well, this was our one-dimensional array of 2 elements x with basically a dot product with a 2x2. So what do we need to do that's different? Well, essentially, if we want to multiply, or rather grab our x tau G, we're going to be doing x matrix multiplication tau times G. Because at the end of the day, G and tau G are both 2x2s. So you're going to be doing the same thing either way. And remember, this is dot product because it is a sum, as mentioned right here. That is a sum. So again, sum of the corresponding values following the precedent I sent here with the dot product of x and g. I feel like we kind of get the point. I don't think it's worth trying to do this again just for tau and g, but hopefully that makes sense now. Yeah, let's go ahead and go code that out for now. So it kind of makes sense. I'm not getting too ahead of myself. So how do we want to do this? If I split it, something like that. Here, green, this. Yeah. Is that how I want to do it? Sure. Okay. So we'll go down here. And yeah, we had our xg term. So let's do xg is equal to, what did we say it was? Matrix multiplication of g, because it was a dot product. Essentially, if we did a sum and a multiplication of the corresponding after each k iteration. So x, and we use the @ sign for matrix multiplication. Oh, that is a lot. What is happening here? Okay. So I'll shift enter on that. Then we also had our x tau g, which was this numerator. We have, let's go ahead and split this, make sure it should still output a 1x2, perfect. I guess technically this is, I think it says this is a one-dimensional with 2 elements. Yeah, so it's just 2 elements. But note that it does retain the same identity as, am I not scrolling on the, oh yeah, okay. I guess I'll write here. Note that I labeled here the columns are I equals 1, I equals 2. And remember, A was essentially index 1, B is essentially index 2. So the identities of A and B boil down to being I equals 1, I equals 2. So this will be important later on the second term, or we'll need to decide basically if we need to do a transpose because the rows and columns don't match. And also which rows and which way, I guess, if you want to broadcast along the rows or columns depending on the indice or index j, or I guess in this case I. So again, depends on your index. So that's xg. And then we also said we had our tauij, which was essentially a 2x2 because it was a straightforward multiplication. It's kind of bothering me. I'll kind of switch this over. So funny if you can see that. But yeah, I'll kind of moved it over. Hopefully that's fixed. Okay, so yeah, we found that tau times g is just a 2x2 because the matrices are identical. And then now if we try to do x tau g, now that was the same thing as doing xg, where it's a matrix multiplication of our one-dimensional element with, or a one-dimensional array with 2 elements times a 2x2. So again, this should net us another 1/2. So x tau g is equal to x matrix multiply parentheses tau times g. We want to do tau times g first, and let's go ahead and display that. It should be another 2 element. So perfect. And obviously to get our full term here for the I switch to get our full expression here for the first term, I'm just going to divide. Since now we have our numerator and denominator, we do x tau g divided by xg. And that just helps us limit our writing further. So x tau g, I guess, divided by xg. And then I'll write that again, basically. X. And 1/2 divided by 1/2. Again, straightforward because well, in this case, they're not even matrices. They're just 2 elements divided by 2 elements. So again, we should get 2 elements. If we go ahead and display this. And remember that they both have identity of I, where it was shown here in our first kind of visual walkthrough that the 2 components were identities matching to the column. So yeah, we still get our columns there. Awesome. Now, the kind of tricky part here for the tau expression. So if you kind of look at this a little further, I guess I'll switch to my iPad here. So kind of looking at this expression a little further, decides to load, here we go. So if you notice, our second term here, especially this one, is pretty much identical to our first term. And don't let the indices bother you. Remember that the values are pretty much the same. It's just how they're being iterated. So if you look at this, they're identical in the case where instead of, well, I guess what we care about is the not the order, but the letters that show up in the fashion as they're multiplied here. So you can see that for our x's, taus, and g's, they follow the same, I guess, indexing. Not necessarily the same, but similar indexing to the letters used in our first term, where instead of j's for our rows of tau and g, now we have m, and also obviously our x is also m. And then at the bottom here, well, this is still k, but now our column is j. So that's the column is for j is the identity that we care about the most here. We need to make sure that those line up. So we're keeping the identities the same, but again, you can see how it's kind of similar where, well, you still use k on the bottom denominator, but now we use j instead of I compared to the first term. So I was used for the first term for the columns, and then now in the second term on the right, j is used for the columns. So we just need to be very consistent with our usage. So essentially, what I'm going to say here is, or what I wanted to say is this right-hand term is basically the same thing as this term here. So what we got, remember, it was a 1 by 2 at the very end. This I circled this term on the, I guess the only circled term on there right now. Now that I erased it, this is a well, it's a one-dimensional array, 2 elements. And then this tau, remember, at the very beginning, this is the tau that we defined at the start, and this was a 2 by 2. So if I try to subtract a 2 by 2 from a 1 by 2, well, technically it's not a 1 by 2 yet, it's just a 2 element. So we want to make sure we broadcast this. This is where the idea of broadcasting comes in. We want to make sure, I guess it's better if I kind of code this out on Python. So I'll try to do an example here. Let's do something like, how do I want to do this? So I'll make an array, call it A. So A equals, so this is just giving me evenly spaced intervals. So yeah, evenly spaced values within an interval. So I'll just say from 0 to 0 is the default. I'll say, what do I want to say? 6 maybe. So I'll try to do, is that how I want to do it? Now let's do a bigger one so I can do multiple examples. So I'll do a 3 by 3 by 3, which is quick maths, 27. We look at that, that's just, again, evenly spaced intervals. I'm going to go ahead and reshape that to a 3 by 3. So reshape 3 by 3 by 3. And now if I print that, it should be essentially that. I'm telling the truth when I do a dot shape 3 by 3 by 3. Awesome. So basically what I want to do to showcase this idea of broadcasting, I'm going to make, well, I guess I'm going to divide this by another array. And let's make it a, I guess, 3 element, so we can kind of see, here, let's do it down here. Call it something, so B equals that. It's an array of, let's just do 1, 2, 3. So if I want to add A to B, it should let me do that. Sure, this is what I'm saying it is. So if I actually take the shape of that, it should just be a 3 element. So you'll notice that it has a potential, well, I guess I should explain what broadcasting is. So broadcasting, I guess visually this might work, so I keep on switching back and forth here, sorry about that. But this idea of broadcasting is that it allows us to match dimensions and do kind of a universal operation across the matrix. So if I do something, now I'm doing another example, so sorry about that. I don't know, a 2 by 2 plus a, I guess the most simple example you can think of is obviously just one number. So it's a 1 element, not even, well, I guess 1 dimensional array. So if I did something like pretty obvious, like 1, 2, 3, 4, what you would expect if you added 1, well, now it's 2, 3, 4, 5. So that's essentially, that was broadcasting, because now we were able to change this 1 dimensional array. Now essentially what that was doing is changing it to a matrix that would match that 2 by 2. So instead of just a 1 dimensional array with 1 element, now it was a 2 by 2. So, and then now that is just a straightforward addition. So that's how that's basically in a nutshell what broadcasting is. But in terms of something maybe not as not as, I don't know, straightforward or easy to see as that, we'll be using a 3 by 3 by 3 to showcase that. So now I have a 3 element, and if I add this to B, or add A to B, it should be pretty straightforward here. Now it has added 1, 2, 3, possibly. Did I do that wrong? Let's see here. It might have only added, hold on here. I think I'm thinking wrong. So 1, 2, 3. So it did add across 1, 2, 3. So essentially what happened, we across the rows of each one, we added 1, 2, 3. And that makes sense because our matching array was just a 3 element, and we had a 3 by 3 by 3. So there were multiple ways this could be a broadcasted. It could have broadcasted this way. It could have broadcasted vertically. And what I want to do is, let's think about this. If I reshape it into a, I wonder if this would work if it was reshaped into a, let's say 1 by 3 by 2. Or maybe, let's do 2 by 3 by 2. Oh yeah, there's not enough numbers. What am I thinking of? This work? I think I might have flubbed my example here a bit. You know what? I'm trying to think if it's worth even showing this. I think my main point with showing this is how to add another axis. So we use something called list none. Yeah, I don't know if it's worth. I mean, I can mess around with this, but I mean, even if I put something that it can work, I mean, this will already be broadcasted. Because so the idea of broadcasting again, the dimensions have to match, or you use a 1 to match the number of dimensions. And across the ones, it will be broadcasted. I mean, if I add it again, it will be the same outcome because it already worked the first time. It already broadcasted. So I guess this isn't the best example, so sorry about that. I guess what I do want to show while I'm here is the idea of adding the one axis. So if I have 3 here, let's just forget about this since I'm kind of not making sense. So I have, again, the shape was 3 by 3 by 3. So if what I was talking about, so we could add the axes of 1 so that it was able to be broadcasted and was able to divide easily or do whatever operation. The idea was that if we can add a 1, it will be able to work. And if it didn't have that the 1 axis, then it wouldn't work. And how we did that is using the index, so none, then you go colon. And actually, if I just put none here, it should add the 1 in front. So if I do shape, put 1 3 by 3, perfect. And then depending on where you put your colons is where you put the 1 axis. You're adding another axis of 1. So if I put it at the start and comma, it should switch these, and now we'll have 4, but now the 1 will be in the middle. So, yep, perfect. And it actually omits the rest. So even if I don't put it, it obviously does it. But if I put them in, it's the same exact thing. But remember, if you put too many, it'll yell at you and say, it's not enough. Maybe a little slow. There we go. Yeah. You did too many dimensions. So again, it omits it if you don't have to put this. So if you see me doing something like this, that means I just omitted the rest and I put the axis of 1 in front. So that'll be important. Here on, it says my saving failed. Good, let's check. Come on. I'm trying to think if I had another example where I could divide it. I wonder, because if I did a 1 by 2, then it wouldn't necessarily match up. I'd have to turn it into a 1, which I don't think would make sense. I mean, we could try. Why not? What? I'll try it. If it works, I'll explain it. If it doesn't, I'll just move on. So I'll pause it here. Okay, I think I was trying to do too much in my last example. I think the main point of that last example was just for me to show off where I could put the none and like that syntax for adding that new axis of 1. Essentially, with broadcasting, so here I made another array. Now it's a 2 by 3 instead of a 3 by 3 by 3. And I'm dividing this by an array of 2 and 3. So that's a 2 element or 1 dimensional of 2 elements. Now it works if I reshape this array of 2 elements into a 2x1, but notice that if I don't have this here and I don't reshape it, it will not let me broadcast. It says it right there. You cannot broadcast together with shapes of 2 and 3. So again, to broadcast, we need to match, the dimensions need to match, or we have a 1 in place of dimensions that don't match. Usually if the dimension is lower, then we want that to be a 1. So we have a 2 here, so that should match this 2 here. So all I'm doing, instead of reshaping it, I can do something like the none, where I add a 1 axis on the end here, and I put a colon at the front, so we add it last. That gives me, should give me the same thing if I did the reshape here. So let's actually check that. Reshape, I think I did 2x1, so it matches, right? Yeah, so it's the exact same thing. So instead of reshaping, or where the goal is actually to just add a axis of 1. So that's that whole tangent right there. Go ahead and delete all this. Yeah, so I think the point we're getting into is that the tau, let's see, I'll have it up here, and so this tau is a 2x2 and subtracted from a 2 elements. So I think that's pretty similar to what we were doing earlier. So we want this 2 to match, but in our case, the identities of the row and columns matter a lot. So if we try to think of this as which way we want to broadcast this, well, the identity of this x tau g over xg, remember that is just the index of j, and that's what we saw from our xg like visual representation of our matrices, where our 2 values were determined from the columns. In this case, it was I for the first term. So obviously for the right-hand term, second term, the column is index is j. So this 2 element, these 2 values we get from the circled in red right here. Do it again, why not? Those 2 values we get are index relating to that, well, identity of j. So in this case for tau, well, ij, j is our 2. So we want to make sure, or j is our column of 2. So we want to make sure that our j's match here. So this is j and this is I. So if we want j to remain being a column, well, we have to broadcast along the row. So that's what we're going to do. We're going to add a axis of 1 in the front. So I'll do something like, again, a lot of switching over. So it was tau minus our x tau xg, and x tau, it goes x tau g, sorry, over divided by xg. And this will work, but we want to make sure that it broadcasts correctly. So to do that, remember, we do the axis of 1 in front. So let's actually show that here. So if I do shape, it should give me 2 elements. And now if I put the x of 1 in the front, it should be now a 1/2. So that's all we're doing here. Straightforward multiplication right after that. So what's next? Going back again to, so after tau, we divide by xg over here. And dividing by xg, well, let's, how do we want it? But hopefully this makes sense. I'll go ahead and erase it. So remember, we were just adding an axis of 1, so we could broadcast this correctly, matching up our j columns. So now if we want to divide by xg, well, remember xg, that's just a 2 elements again. It was, well, same exact thing as what we did here. So it's a 2 element, 1-dimensional array. Again, we should broadcast, well, remember that our tau minus our, well, this term is a 2x2. So if we want to divide by 2x2 by a 1 element, same exact thing, we want to broadcast along. Remember, it was across j. J is the columns. So if j is the columns, tau, j, we want to broadcast along the row once more. And that's because, again, the identity of this term, xg, is denoted by the column value. So that's why we broadcast along the row to keep it same. And broadcasting along the row just means, again, we add an axis of 1 in the front. So if we want to divide by xg, we go ahead and do that. Let's go here and here. So all I'm doing here, again, we divide by xg, and we put our at index of 1 in front. So again, xg by itself, 2 elements. If I put the index of 1 in front, 1 by 2. So again, another 2 by 2. So I think the last thing was multiply by g, I think. Let's go ahead, double check that. Let's just keep going. Why not? So I'll go ahead and erase this again. Sorry if it's a little confusing. But all we're doing here is making sure it broadcasts in the correct direction, even though I believe even if you remove the index of 1, the none in brackets, it should actually still work. It actually, I think it automatically broadcasts along the row if you don't put anything. But let's not leave it up to chance like that and make sure it's properly put in. So yes, now that we have pretty much this entire term, all we're missing are these 2 terms. So let's ignore the x for now and focus on the g. Well, g, remember, is a 2 by 2 matrix. And if we're multiplying a 2 by 2 matrix, well, remember what we just got after dividing by our xg term here. Tau, well, let's just go start from the beginning. Tau was a 2 by 2. We broadcasted that after subtracting in our parentheses term here. So that was another 2 by 2. The 2 by 2 divided by xg here on the bottom. Oh, that's not what I wanted to do. Xg term here on the bottom. Well, that was a 2 by 2 divided by a 2 elements, where we added the axis of 1 in front, so that it became a 2 by 2 divided by another, well, divided by a 1 by 2, so that it could be broadcasted. And again, it was just another 2 by 2. So at the end of the day, we have a 2 by 2 times a 2 by 2. And we can actually check this. I don't know why I'm saying all of this when we could just go ahead and do something like this. Well, also you can just see it right here. This is a 2 by 2, but just you don't take my word for it. Yeah, so 2 by 2. So all we're gonna do is, again, straightforward multiplication. If it's times g, 2 by 2 times a 2 by 2, that's just g. And I'll put that in another parentheses because why not? Now here's the kicker. Every time we've multiplied x, we did a matrix multiplication because we had to worry about that summation sign, as well as matching up our indices of rows. But in this case, you can see when we add in our x times g, now the element that we've been worried about so much before is now in the column section. Before, the corresponding section with the x was in the rows. So I don't know the best way to. I'll go ahead and write this out. So it was x. I don't even know what it was. Xj. The summation j n equals 1, and xj times gij. So we can do our little table again. So now that the indices are flipped, well, we still have our x1, x2. That hasn't changed. We're still picking up from 1 to 2. Now we multiply this. Well, essentially it's going to be another dot product because we see a summation sign, and we're multiplying across different indices. So this is our G matrix. So if we number our G's as usual, the only difference is how we're going to sum them up. Sorry, that's wrong. That should be 2. So row 2, column 1, row 2, column 2. So now if you see, well, we always match them up when J is the same. And if J is a column for G, that's where we need to match it up. So something like, how do we want to do this? For J equals 1, maybe? Sure. For J equals 1, we have x1 times g1, and I is kept the same since we're not taking up J. So I is 1 here, and then now I have a 1. Now here's the difference. We see x2, I remember is a row, so I remains 1. But then j is a column, so we tick up to j2. Did I do that right? I'm sorry, this should not be j, it should be for I, as we did before. But now you're seeing the difference here. So for I equals 2, same thing. If we have x1j, j equals 1, but now the I is 2, but our j is 2. Did I say that right? J is 1 still here. So I guess I should label this since I'm confusing myself. So j equals 1 and j equals 2. So remember, j is the columns for our g term now, and x remains the same. So x2, g I is row, so I is 2, and then column is matching up to the j equals 2, so j equals 2. And now you see that is not quite the same of what we had before, where in this case, instead of doing what we did before, where it was up and down, now to match this up, G11, G12, we're actually doing this. And now we add these two together, the blue and the red. So a little different from what we had before. And we can do it this way, but an actual easier way to do it would be if we could somehow change this back into ji. And to do that, we do something called a transpose. So a transpose, well, what that does, you can see it right there, it kind of flips the rows and the columns. So if I flip the rows and the columns, now, how do we want to do this? I'll go ahead and kind of make a section off here. So if now we're trying to do the transpose of that, it'll be the same exact thing as what we did before, a dot product where the rows, columns match, or essentially you multiply the rows across the columns of the other. So now if I move, here, let's erase this so we can see what we were looking at before. So if I move this row down here, I would have G11, G12. And if I move this row to this column, we have G21, G21, G22. So now if I still want to do our same multiplication we did across like this, now if I want to do x1, basically if I want to do this, x1 g11 and x2 g12, I can now do the dot product where it's, I guess we should keep the same color, where now it's the blue is vertical, like so. So g11, g12 is now like that. The blue is overlapping, so I don't like that. I'll switch colors again. So now we can do across, like so. And now this is the actual dot product, just like we had before, where we had, I guess we should do same colors. So green, x1, x1, x2. Well, we said it was g1, 1, and g2, 1. Oh no, did it stop? Yeah, like my Wi-Fi is freezing for me on me a bit. So those G11 and G21. So G11, G21 is like that. And again, X1, X2. We had G12 and G22. So G12, G22. So exact same pattern now. Now we call this the dot product. And again, our one element, I guess one dimensional array, 2 elements, and then our 2 by 2. And that just gives us a dot product. So it's a 1 by 2, or 2 elements, 1 dimensional array. Hopefully that should be the end of it, of all that visual matrix drawings. All I should do. Let's go back. So we want to multiply by x right here. do a matrix multiplication, essentially the dot product, we need to make sure we do the transpose. That gives us our, again, I said one-dimensional array, 2 elements. So what are we doing? Well, we wanted to define the function for gamma and get this expression to be the same as our, well, what the correct code says, essentially. So what I'm going to do, I'm going to combine a bunch of these. So let's see, I can delete this, delete that, hopefully kind of clean up here as I wonder if I can merge all these together. That might be better. So, oh man, did I delete that? I hope not. I should learn the shortcut. Merge, yeah, there we go. So, how are we gonna do this? Clean this up later. Let's just focus from the start to the beginning. So we have our function that we want to define as gamma. Closer. As gamma, and again, this takes a liquid mole fraction and our temperature. Same exact thing as up here with our imported function from chetools. So that's a function. Now we have our expressions we defined before, and I guess I should indent all of this. So that's control bracket, something I do know. Right bracket for indent to the right, left bracket for indent to the left. So we define our tau, define our g. We have xg, which was the matrix multiplication. So these are 2x2s. This is a 2 element. X tau g should be a 2 element as well, because we did a matrix multiplication. Then x tau g divided by xg, again, that's the 2 elements divided by 2 elements, or 1x2 by 1x2. Now here is our right hand side. So I guess what's better is if I do this and that. So if we look back at our expression here, right here, we see that now we have our left hand side and now we have our right hand side. So this is actually our right hand side. So what I'm going to do is never have enough parentheses. So we want to actually return this, and remember that this was since it's a natural log, if we want to isolate this activity coefficient, we take the exponential. So it'll be something like returning the NP exponential. So if this is the right hand side, or I guess second term, we want the left hand side, which was just this expression. So I guess add another parentheses, put it in back. That's me. Go. Now I just do copy here, paste here. And hopefully this all works. So let's double check. X tau g over xg. And then we have our plus x matrix multiplication. And then, of course, this was our transposed after we multiplied by g inside. And then before we multiplied by g, we divided by xg. Remember, we chose to showcase purposefully the broadcasting along the first axis, the rows, so that the j's, the identity of the j columns match. And then same exact thing when we did a different with tau, where tau was a 2x2. So hopefully, if this all works, go ahead. Hope it works. Okay, didn't yell at us. Nothing bad yet. And let's go ahead, call our function. Apply it with our x and t, liquid mole fraction, and temperature. Hopefully this works. Okay, put our numbers here. Oh my goodness, first try. Oh way, we got it. Okay, that's awesome. So that means, well, trusting that this code is correct, we got the correct activity coefficients for isopropanol and water. So one last thing here, just kind of an overview. Going back to iPad. So we were able to, luckily, get our function right after doing all the matrices, our visual representations. Hopefully that all made sense. The main idea was matching with broadcasting, where we had to match the dimensions correctly, broadcast it along the correct dimensions so that our identities were kept the same and consistent, and also with straightforward element multiplication, division, subtraction. That's how we were able to simplify this massive expression down. I believe in the future this will be used for, we can do now our, if you remember from our first couple round of videos where we did bubble P, dew P. So now we'll be doing bubble pressure, bubble temperature, then of course dew pressure and dew temperature with this gamma activity coefficient with Raoult's law, which is now for ideal cases. We write the Raoult's law. We write it was liquid mole fraction component with now gamma I, the saturation vapor pressure of a component, so pi set times y, our vapor mole fraction times our total pressure. That was always equal to our partial pressure, but we never use that much. So kind of see where we're going here. We're going to be using our gamma, this activity coefficient, to essentially graph a new binary XY diagram with the help of our bubble pressure, or I guess bubble and dew pressure and temperatures functions. So look forward to that if that gets, that's something we get to do here. So I believe we did everything. So just another showcase at the end. The our final efforts here. So this can be, yes, showed at the end and checked. Yeah, thanks for watching.